Standard differential calculus relies on two foundational tools. On the left, we have the power rule. On the right, the exponential rule. The power rule is restricted to instances where the exponent is a constant integer, such as x squared or x cubed. The exponential rule requires a constant integer base, as seen in 2 to the power of x. An anomaly occurs when a system features an independent variable in both positions. These are tower functions, defined as y equals x to the power of x. Attempting to force this structure into standard rules causes a mathematical failure state. The tower function violates the requirements for a static base or a static exponent. To differentiate these dynamic pairings, standard algebraic rules must be replaced by logarithmic transformations. Recognizing the absolute boundaries of standard calculus is the prerequisite for modeling systems where no variables remain static. Solving these requires the logarithmic differentiation workflow. We begin by applying the natural logarithm to both sides of the tower function equation. This utilizes the logarithmic power identity. Taking the natural log of the expression unhooks the exponent, converting it into a scalar multiplier. Step 2 executes implicit differentiation. The left side's chain rule transforms natural log of y into 1 over y times dy dx. The right side combines product and chain rules, yielding g prime times natural log of f plus g times f prime over f. In step 3, we isolate the derivative algebraically. We multiply the right side expression by y, then finalize the formula by substituting the original tower function back. This workflow functions by demoting an exponentiation operation into a multiplication problem. Verify this on y equals x to the power of x. Step 1, natural log of both sides gives natural log y equals x times natural log x. Step 2, implicit differentiation yields 1 over y times dy dx on the left and natural log x plus 1 on the right. Step 3, multiply by y and substitute the original function back to resolve the derivative. This derivative identifies the instantaneous rate of change for a function where both the base and the exponent are coupled variables. Aerospace engineers use these derivations to model the forces of supersonic atmospheric entry, specifically calculating maximum aerodynamic drag, or max-q. This requires differentiating exponential atmospheric decay against accelerating dynamic pressure, tracking altitude and velocity as coupled time-dependent functions. Optimizing a rocket's structural mass relies on variations of the Tsiolkovsky rocket equation. Maximizing payload requires setting up sensitivity matrices that rely on logarithmic derivatives. This foundational orbital mechanics equation was pioneered by Konstantin Tsiolkovsky. In electronics engineering, these calculations are applied to the dynamic behavior of p-n junction diodes. William Shockley established the model for semiconductor conductance, which follows a strictly exponential current voltage path. To calculate a circuit's small signal dynamic resistance, engineers evaluate the inverse of the exponential derivative found in the Shockley diode equation. In analog circuit design, log derivatives define fractional sensitivity. This isolates the specific percentage change in system performance relative to a percentage drift in component tolerance. From the extreme limits of aerodynamics to the micro-tolerances of semiconductors, log derivatives define these critical hardware boundaries. In systems engineering and machine learning, logarithmic differentiation is the core mechanic for optimization. Optimization for multi-class classification networks relies on cross-entropy loss. Backpropagation algorithms update neural network weights by computing the gradient of this specific logarithmic loss function. Because softmax activations produce exponential probability distributions, backpropagation depends on these specific log derivative pairings. When modeling hardware resources for high-throughput scaling, performance limits like O of n log n scale alongside log derivative metrics. Modern algorithmic weight updates are mechanically driven by obtaining the gradients of these functions. While manual derivation builds intuition, modern engineering executes these calculations symbolically. Python libraries like SymPy automate the logarithmic differentiation workflow, executing symbolic derivatives at scale. Encoding these mathematical relationships allows engineers to calculate sensitivity matrices across thousands of variables simultaneously. Standard calculus logic fails when exponents are dynamic. Logarithmic differentiation provides the mechanical workaround required to calculate rates of change in systems where nothing remains static.